March 7, 1943. Occupied France. The Atlantic coast lies under a sky the color of cold iron, flat, heavy, and indifferent to everything happening beneath it. Along the harbor at WWII, a structure stretches like something carved not by engineers, but by time itself. Massive, silent, immovable. 11 submarine pens, each one buried beneath nearly 7 meters of reinforced concrete, sit like a challenge to the entire idea of aerial warfare. For months, the Allies had tried to break them. The Royal Air Force had come first. Then the Americans. Waves of bombers filled the sky, engines roaring, bomb bays opening, thousands of tons of explosives raining down. The mighty Avro Lancaster dropped everything it could carry. High explosive bombs slammed into the roofs of the pens. And nothing happened. Not nothing, exactly. The bombs exploded. Fireballs rolled across the surface. Shock waves cracked through the air. But the concrete beneath them did not break. It didn't even meaningfully weaken. The explosions looked dramatic from above, but to the pens themselves, they were little more than noise. The bombs bounced, skipped, detonated harmlessly, like pebbles thrown at a fortress. Inside those gray, bunker-like catacombs, German U-boats were being refueled, repaired, and rearmed without urgency. Crews moved calmly through their routines. Officers reviewed patrol schedules. Submarines slipped in and out of the Atlantic almost at will, heading out to hunt Allied convoys with devastating efficiency. The Battle of the Atlantic was reaching its breaking point. In just the first 3 months of 1943, German submarines would sink over 100 Allied ships. Food, fuel, ammunition, everything Britain needed to survive was being cut apart shipment by shipment, and the structures protecting the submarines responsible for this destruction remained untouched, unbreakable. That was the problem. And it wasn't a problem of bravery. It wasn't a problem of resources. It wasn't even a problem of accuracy. It was a problem of physics. By 1943, Allied bombing doctrine had quietly run into a wall, one that planners before the war had never truly accounted for. The entire theory of strategic bombing depended on the assumption that enough explosives dropped on a target would eventually destroy it. But reality was different. Certain targets simply could not be destroyed with the bombs that existed. The German U-boat pens were the most obvious example, but they were far from the only ones. Across occupied Europe, the Germans had constructed a network of hardened installations, reinforced concrete bunkers, deep railway viaducts, fortified launch sites, underground fuel depots. Structures designed not just to resist attack, but to ignore it. Standard bombs, like the 1,000-pound general-purpose bomb used by the RAF, worked through blast and fragmentation. They exploded on or near the surface, sending shockwaves outward through the air. Against factories, rail yards, and cities, this was devastating. Against meters of reinforced concrete, it was meaningless. The RAF tried to compensate the only way they knew how, by dropping more bombs. Over WWII alone, thousands of tons of explosives were released. The surrounding city was reduced to rubble. Civilians fled. Entire districts disappeared. But the submarine pens? They remained. German crews continued walking into them every morning, as if nothing had happened. Repairs continued. Submarines launched. The war at sea went on. The truth was brutal in its simplicity. A bomb exploding on the surface transfers most of its energy into the air. The shockwave expands outward, dissipating rapidly. The concrete beneath absorbs what little energy reaches it, distributing the force across its massive structure. To destroy something like that, you couldn't just hit it harder. You had to hit it differently. You needed a bomb that didn't explode on the surface. You needed a bomb that penetrated deep into the structure or even beneath it and then exploded. A weapon that turned the ground itself into part of the attack. The idea existed. On paper, it made sense. But turning that idea into something real, something that could actually work in combat, that was another matter entirely. And that's where one man entered the story. Wallace. Most people would later remember him for something else. The famous bouncing bomb, the weapon that skipped across water and destroyed dams in one of the most daring operations of the war. But that wasn't his true obsession. That was just a step along the way. For Wallace, the real problem had always been bigger, Much bigger. He wasn't trying to destroy dams. He was trying to answer a question that had no clear answer at the time. How do you destroy something that cannot be destroyed? How do you destroy something that cannot be destroyed? That question stayed with Barnes-Wallace long before the war had reached its most desperate phase, long before the U-boat pens at Loria had proven the limits of conventional bombing. Even in the late 1930s, Wallace had already begun thinking beyond the accepted rules of warfare, beyond the idea that bigger explosions automatically meant greater destruction. His insight was both simple and revolutionary. You didn't actually need to destroy a structure directly. You need to shatter from above or tear it apart piece by piece. Instead, you could attack something far more fundamental, the ground beneath it. If you could deliver a powerful enough explosion deep underground, the earth itself would become the weapon. The structure above wouldn't be blasted apart in the traditional sense. It would collapse inward, as if the ground had suddenly betrayed it. This idea drew from seismology, the science of earthquakes. When a large explosion occurs underground, it doesn't just create a crater. It generates a shock wave that travels through surrounding earth, spreading outward in all directions. Unlike surface blasts, which dissipate quickly into the air, these underground shock waves carry enormous energy through dense material. And reinforced concrete, for all its strength, is not designed to withstand that kind of force from below. Concrete is incredibly strong under compression from above. That's what makes it ideal for building bunkers, fortifications, and submarine pens. But when pressure comes from multiple directions simultaneously, when the ground itself begins to shift and ripple, the structure loses its advantage. It doesn't explode. It simply collapses. To make this concept work, however, required something that didn't yet exist, a bomb capable of penetrating deep into the earth before exploding. And that requirement created a cascade of engineering challenges. The bomb would need to be dropped from a very high altitude to build enough speed during its fall. It would need to be shaped perfectly to minimize air resistance and maintain stability. It would need to strike the ground at a near vertical angle, preserving as much of its velocity as possible. And most importantly, it would need to survive the impact without breaking apart before detonation. Wallace calculated that such a bomb would need to be enormous, far larger than anything currently in service. He envisioned a weapon weighing around 10 tons, dropped from heights exceeding 40,000 feet. In reality, even the best aircraft available, including the Avro Lancaster, rarely operated above 20,000 feet in combat conditions. That meant every aspect of the design had to compensate for this limitation. The bomb would have to be not just heavy, but aerodynamically perfect. It would need to behave less like a falling object and more like a projectile, stable, controlled, precise. The solution was elegant. By designing the bomb with slightly angled tail fins, Wallace ensured that it would spin as it fell, much like a rifle bullet. This rotation stabilized its trajectory, allowing it to maintain a straight, vertical descent. Instead of tumbling through the air like conventional bombs, it cut through it cleanly, gaining speed and accuracy as it fell. Years of design, testing, and refinement followed. The result was a weapon unlike anything that had come before it. The Tallboy. When it finally entered service in 1944, the Tallboy was a masterpiece of engineering. Measuring over 6 meters in length and weighing more than 5,400 kilograms, it was both massive and precise. Nearly half of its weight consisted of Torpex explosive, a compound significantly more powerful than TNT. But the explosive itself was only part of the equation. The casing of the Tallboy was just as important. Forged from high-tensile steel, the same type used in naval gun barrels. It was designed to withstand extreme forces. When the bomb struck the ground at high speed, the casing had to remain intact long enough for the bomb to penetrate deep below the surface. Only then would it detonate, unleashing its energy where it mattered most. Manufacturing such a weapon was extraordinarily difficult. Each Tallboy required over 100 hours of precision machining. The tolerances were so exact that standard production methods couldn't be used. Every component had to be carefully crafted and assembled under strict quality control. Even filling the bomb with explosive was a delicate process, requiring controlled temperatures to prevent imperfections that could compromise its performance. In total, fewer than 1,000 Tallboys would ever be produced. They were expensive, time-consuming, impractical by the standards of industrial warfare. But they didn't need to be mass-produced. They only needed to work. And to deliver this weapon, the RAF turned to one of its most elite units, No. 617 Squadron RAF. Already famous for their role in the dam-busting raids, the squadron was now tasked with something even more demanding: precision attacks using one of the most complex weapons ever created. Their aircraft were specially modified Lancasters, stripped of excess weight, reinforced to carry a single Tallboy, and optimized for a high-altitude performance. Each plane carried just one bomb, one chance, one target, because when a Tallboy hit, it didn't just damage its target. It changed the ground beneath it. It changed the ground beneath it. And when that ground moved, nothing built upon it could remain the same. That was the theory. Elegant, precise, almost inevitable on paper. But war does not reward theory. It rewards results. And for the Tallboy, the moment of truth arrived not in laboratories or design rooms, but in the dark skies over occupied Europe. The unit chosen to deliver this unprecedented weapon, No. 617 Squadron RAF, understood better than most that success would depend not just on the bomb itself, but on the precision of its delivery. Dropping a weapon designed to penetrate deep into the earth required accuracy on a level rarely achieved in wartime bombing. A miss by even a few dozen meters could mean the difference between total structural collapse and near-complete ineffectiveness. Their aircraft, modified versions of the Avro Lancaster, had been stripped down to their essentials: armor removed, gun turrets reduced, weight sacrificed wherever possible. Because every kilogram mattered when you were carrying a single 12,000-pound bomb that would decide the outcome of the mission in a single moment. Then came June 1944, just 2 days after the Allied landings in Normandy. While the world's attention was fixed on the beaches, another operation was unfolding in the skies above France. Quiet, precise, and almost entirely unknown to the public. 19 Lancasters lifted off under cover of darkness, their destination the Saumur Railway Tunnel in the Loire Valley. It wasn't a glamorous target. No headlines would be written about it, but strategically it was critical. German armored divisions were expected to move through that tunnel, reinforcing positions that could threaten the fragile Allied foothold in Normandy. If the tunnel remained operational, the consequences could be severe. As the bombers approached their target in the early hours of June 9th, the tension inside each aircraft was absolute. There would be no saturation bombing, no second passes, no margin for error. Each crew had one opportunity to place their Tallboy exactly where it needed to go. And then, one by one, the bombs were released. Falling from thousands of meters above, the Tallboys cut through the air with terrifying speed, spinning slightly, stabilizing themselves, accelerating toward the earth below. From the ground, they would have been almost invisible, just dark shapes descending silently before impact. Several struck the hillside above the tunnel, penetrating deep into the earth before detonating. The explosions didn't produce the dramatic surface blast typical of conventional bombing. Instead, they generated something far more destructive, a violent upheaval beneath the surface. One bomb went further. It punched directly through the roof of the tunnel and exploded inside. The result was immediate and decisive. The tunnel collapsed, blocked completely, rendered unusable for the remainder of the war. German reinforcements were delayed, diverted, disrupted. The Tallboy had proven that Wallace's concept worked, not just in theory, but in combat. But the real test still lay ahead, because the Saumur Tunnel, for all its importance, was not the ultimate challenge. The real challenge still stood along the Atlantic coast, unchanged and seemingly untouchable: the U-boat pens. By September 1944, preparations were complete. The same structures that had once defied thousands of tons of conventional bombs were now about to face something entirely different. This time, the attack would not rely on blasts alone. This time, the Earth itself would be turned against them. Lancasters from both 617 Squadron and No. 9 Squadron RAF approached their targets, massive submarine bases at Brest and La Pallice. Using advanced targeting systems, including the stabilized automatic bomb sight, they aimed for something unprecedented: precision against structures designed to resist destruction. The bombs fell, and for the first time since the war began, the pens did not simply endure. Tallboys struck the concrete roofs, not exploding on impact, but driving through them, punching deep into the structure or the ground beneath. A moment later, the detonation came. What followed was not a surface explosion. It was a transformation of the ground itself. Subterranean shock waves surged outward, creating massive underground voids, camouflages, that destabilized everything above them. The reinforced concrete, so effective against traditional bombing, suddenly became a liability. Sections of the pens shifted, cracked, and collapsed inward under forces they had never been designed to withstand. Inside, the effect was catastrophic. Massive slabs of concrete fell. Structural supports failed. Sections of the facility that had once been considered completely secure became death traps. At least one U-boat was crushed where it sat, entombed beneath the very structure meant to protect it. Others were damaged beyond repair, not by direct hits, but by the collapse of the environment around them. For the crews inside those pens, the psychological impact was just as devastating as the physical destruction. For years, these structures had represented safety, a place where the chaos of the war could not reach them, a place where bombs fell harmlessly above, where thick concrete separated them from the violence outside. Now that illusion was gone, because the Tallboy had done something no weapon before it had managed. It hadn't just damaged the pens, it had made them dangerous. The ground beneath them could no longer be trusted. The ceiling above them could no longer be relied upon. Every creak, every crack, every vibration carried a new and terrifying meaning. The safest place in their world had become uncertain. And in war, uncertainty is often more powerful than destruction itself. The safest place in their world had become uncertain. And once uncertainty enters a system built on confidence, everything begins to shift. Slowly at first, then all at once. What the Tallboy had achieved inside those U-boat pens was not just structural damage. It was psychological erosion. The idea of invulnerability, once broken, could never be fully restored. But while the impact on the German submarine bases was profound, the significance of the Tallboy extended far beyond those concrete walls. Because what Barnes-Wallace had created was not just a new weapon, it was an entirely new way of thinking about destruction. And that difference became even more apparent when compared to what the Axis powers themselves were producing. Germany, despite its advanced engineering capabilities, had not arrived at the same conceptual breakthrough. Their largest operational bomb, the SE-2500, nicknamed Max, weighed roughly half as much as a Tallboy and relied almost entirely on surface blast. It was powerful, certainly, but against hardened structures like reinforced concrete bunkers or submarine pens, it was no more effective than Allied bombs of similar size. They did develop armor-piercing bombs, such as the PC series, designed to penetrate the steel decks of warships. But these weapons were built for a very different purpose. They were meant to breach relatively thin layers of armor and explode within ships, not to drive deep into the earth or collapse massive concrete structures from below. The fundamental idea behind the Tallboy, the use of the ground itself as a weapon, was simply not present in German designs. The same was largely true for the United States. American engineers were actively working on their own penetrating bombs, including weapons like the T-14 and later the M65. These represented serious attempts to solve the problem of hardened targets, but they were significantly smaller and lacked the aerodynamic refinement that made the Tallboys so effective. At around 1,000 pounds, these bombs simply didn't carry the mass required to generate the kind of subterranean shockwave Wallace had envisioned. More importantly, American bombing doctrine at the time emphasized scale over specialization. Large formations of bombers, dropping vast quantities of conventional explosives, were expected to overwhelm targets through sheer volume. It was a strategy that worked well against industrial cities and infrastructure, but struggled against deeply fortified structures. Even advanced systems like the Norden bomb sight, despite its reputation for precision, often failed to deliver consistent accuracy under real combat conditions. There was, however, one American project that came closer in spirit to Wallace's idea, the T-12 Cloudmaker. At an enormous 44,000 pounds, it was even larger than the Tallboy, but it never saw operational service. It remained an experiment, a concept that arrived too late and never fully matured into a practical weapon. In contrast, the Tallboy didn't just exist, it worked. And it worked so well that even the United States would eventually rely on British-designed earthquake bombs, including both the Tallboy and its even more powerful successor, the Grand Slam, when deep penetration strikes were required. But perhaps the most dramatic demonstration of the Tallboy's capabilities came not against bunkers or tunnels, but against one of the most heavily protected warships ever built, the German battleship Tirpitz. For years, the Tirpitz had loomed over the Allied war effort like a shadow. Stationed in Norwegian waters, it posed a constant threat to Arctic convoys supplying the Soviet Union. Even when it wasn't actively engaging enemy ships, its mere presence forced the Allies to commit significant naval resources to monitor and contain it. Attempts to destroy it had failed repeatedly. Submarine attacks, air raids, special operations. None had succeeded in permanently neutralizing the battleship. It was heavily armored, well defended, and positioned in locations that made conventional attacks extremely difficult, until the Tallboy entered the equation. On November 12, 1944, RAF bombers once again took to the skies, carrying the same weapon that had shattered the illusion of safety inside the U-boat pens. As they approached their target, the conditions were far from ideal. Weather, distance, and defensive fire all added layers of complexity to the mission. But once again, precision would decide everything. The bombs fell. 3 Tallboys struck the Tirpitz. They penetrated deep into the ship before detonating, unleashing their immense from within rather than against the surface. The effect was devastating. Massive internal damage, structural failure, uncontrollable flooding. The battleship, once considered nearly indestructible, began to roll. Within minutes, it capsized. The destruction of the Tirpitz was more than just a tactical victory. It removed a persistent strategic threat and freed up Allied naval forces that had been tied down for years. In a single operation, the Tallboy accomplished what countless previous attempts had failed to achieve. And yet, despite moments like this, the overall impact of the Tallboy must be understood carefully. By the time it was used against the U-boat pens in 1944, the Battle of the Atlantic had already begun to turn in favor of the Allies. Advances in convoy tactics, long-range patrol aircraft, and the breaking of German naval codes had significantly reduced the effectiveness of the U-boat campaign. The pens, while still important, were no longer the unassailable strategic assets they had once been. But that doesn't diminish what the Tallboy represented, because its true significance was not just in what it destroyed, but in what it proved. It proved that even the most heavily fortified structures, those designed to resist everything known to warfare, could be defeated not by more force, but by a fundamentally different kind of force. It proved that destruction did not have to come from above. It could come from below. And once that idea existed, once it had been demonstrated in combat, it could never be undone. It could come from below. And once that idea had been proven in war, once the ground itself had been turned into a weapon, it was no longer just an innovation. It was a transformation, a shift in how destruction could be understood, engineered, and delivered. What Barnes-Wallace had unlocked was not limited to a single bomb or even a single war. It was a principle, and principles, once discovered, have a way of outliving the conflicts that create them. But to understand the full weight of that transformation, you have to return, once more, to where this story began. Back to the Atlantic coast. Back to WWII. Back to that gray, indifferent sky of March 1943, when bombs fell in their thousands and achieved nothing. When a U-boat pen stood untouched, unshaken, almost mocking the very idea of aerial attack. Inside those concrete giants, life had continued with routine certainty. Crews drank their coffee. Engineers checked their systems. Submarines came and went like clockwork. Nothing changed. Now move forward. 18 months. October 1944. The same coastline. The same Atlantic stretching endlessly beyond the horizon. The same massive concrete pens still dominating the harbor. But step inside them now, and something feels different. Something is wrong. The ceilings are no longer perfect. In places there are cracks, subtle but undeniable. Sections of concrete show signs of stress, repaired hastily with materials that don't quite match the original structure. The floors in some areas have shifted, just enough to disrupt drainage systems that once worked flawlessly. Water pools where it shouldn't. Machinery sits slightly misaligned. And then there are the markings. red chalk lines drawn by German engineers, highlighting areas considered structurally unsafe, zones where access is restricted, places where men are no longer allowed to work freely, where every movement is cautious, every sound is watched, every vibration is felt, because now they know that the ground beneath them can no longer be trusted. They know that the concrete above them is no longer absolute protection. And in at least one location, the evidence is impossible to ignore: a U-boat crushed beneath fallen concrete, never having left its berth because the berth itself collapsed around it. This is what changed, not just the structure, the certainty. That was the true target all along. Because the hardest things to destroy in war are not the visible ones, not the ships, not the buildings, not even the armies. The hardest things to destroy are the ones deliberately designed to resist destruction, layered, reinforced, buried beneath meters of earth and concrete until they begin to resemble part of the planet itself. And against those things, more of the same force will never be enough. That was the lesson. That was the realization. The answer was never just bigger bombs. It was a different kind of bomb. The Tallboy was not an evolution of existing weapons. It was a complete reimagining of what a bomb was supposed to do. It didn't aim to create destruction around a target. It aimed to place destruction beneath it, to turn the very foundation of that target into its greatest weakness. On paper, it sounded almost philosophical. In reality, it was devastatingly practical. Fewer than 1,000 Tallboys were ever built. They were expensive, time-consuming to manufacture, and required specially modified aircraft and highly trained crews to deploy effectively. By the standards of industrial warfare, they were inefficient. They could never replace conventional bombing on a large scale, but they didn't need to, because within their specific purpose, the destruction of the indestructible, they were unmatched. And their legacy did not end in 1945. Long after they ended, the idea behind the Tallboy continued to shape modern warfare. The concept of deep penetration munitions became a cornerstone of military engineering. Decades later, weapons like the American WWII, used during the Gulf War to destroy hardened underground bunkers, would operate on the same fundamental principle: penetrate first, detonate later. Let the ground do the rest. A direct descendant of Wallace's vision. Today, if you visit the RAF Museum London, you can still see a Tallboy up close. It doesn't look like a conventional bomb. It looks precise, engineered, almost elegant. Its smooth casing, even after decades, reflects the extraordinary craftsmanship that went into its creation. It doesn't scream destruction. It suggests purpose. And if you stand there long enough, looking at it, it becomes easier to understand what made it different. Not just its size, not just its power, its idea. Because in the end, that's what changed everything. Not the explosion, the thinking behind it. Return once more to Loria. The pens are still there today. The town around them has been rebuilt. Life has moved on, as it always does. But inside those massive concrete structures, if you look closely, you can still see the evidence. Slight variations in color where repairs were made, lines where cracks were filled, subtle imperfections in something that was once considered perfect. The scars are still there, written into the concrete itself. They are quiet now, easy to miss, but they tell a story of a moment when the rules changed, when certainty failed, when something that was never supposed to break finally did. Barnes Wallace didn't just design a bomb. He made the ground shake. And once the ground begins to move, everything built upon it must answer. The rest, as they say, is geology. Fire,